Okay, welcome back. What I want to talk about today, excuse me, is about capacitors. And what we need to look at is understanding the concepts of capacitance and determining capacitance values in DC circuits. Okay? Now, when we deal with capacitors, we can use capacitors for a number of things. And obviously there are various values, and remember the capacitance is normally calculated in microfarads, picofarads or nanofarads, which is 10 times 10 to the minus 6, I should say 1 times 10 to the minus 6, 1 times 10 to the minus 9 and 1 times 10 to the minus 12. Now get familiar with those, because those are what we refer to as standard format, okay, in regards to writing microfarads. Now here, what is a capacitor? A capacitor is an electronic device that can store electric charge. Basically, it consists of two plates separated by an insulating material called a dielectric. Now the dielectric can be made up of almost any kind of material that is flexible, and one of the first materials comes to my mind is plastic. Now some of you might be familiar with cling film. The thickness of the dielectric is sometimes about that thick, if not even thinner in some cases. By creating a dielectric of that type, you allow the capacitor to hold a larger charge, and that brings the potential for the capacitor to be handled very carefully, because if it discharges in any incorrect manner, it can actually blow or damage the dielectric internally. So it is in your interest to make sure your capacitors are handled with care at all times. Now we have here a connection coming from one side of the plate. We have here connection coming from the other side of the plate. Now in between here is where your electrostatic charge builds up, and that forms that charge electrode which holds your capacitive charge in between those two plates. Now we represent a capacitor in the circuit by the symbol, and here you can see your symbol, okay? Now what do we mean by a dielectric? Let's take this through step at a time. A dielectric is an electrical insulator that can be polarized by an applied electric field, meaning that we apply voltage to this dielectric, and it will have a response and it becomes polarized in one form or another. Okay. Now when a dielectric is placed in an electric field, electric charges do not flow through the material as in a conductor, but only slightly shift from their average equilibrium, meaning balance, positions, causing dielectric polarization. Because of dielectric polarization, positive charges are displaced toward the field and negative charges shift in the opposite direction. This creates an internal electric field which reduces the overall field within the dielectric itself. Now what that simply means is that by applying an electrical field, we are allowing electrons to become displaced, more polarized on one side than they are on the other. Okay, so we have almost a displacement of electrons, but they're still there. They're just being polarized on one side of the plate more than it is on the other side. If a dielectric is composed of weakly bonded molecules, those molecules not only become polarized but also reorient so that their symmetry axis aligns to the field. This simply means that these will become polarized and they will simply be aligned with the electromagnetic field that exists within the capacitor and align themselves north to south in that sense. Okay. Although the term insulator implies low electrical conduction, dielectric is typically used to describe materials with a high polarizability. The polarization of the dielectric by the applied electric field increases the capacitor's surface charge. And remember that the capacitor surface charge can be quite large. In some cases, depending upon the size of the capacitor, you can have thousands of volts across those terminals. So again, care should always be exercised. And those of you who have had me for health and safety will know that health and safety is paramount in anything that we do in regards to electrics. The main thing is to go to work and to get back home safely. Now here we have the capacitor, and here you see that electron flowing from negative to positive. That's electron flow. Now again, remember that we're dealing in electron flow in regards to capacitors, not conventional flow of current. Okay, so we're dealing with electron flow in regards to capacitors. And here, electrostatic field. Now bear in mind, we have now got, assume a supply to the plates. We now have an electrostatic field build up across the two plates. Okay, and you can see that one is positive and one is obviously negative, but that potential exists between the two plates, and that becomes your charge in due course. Now discharging a capacitor. Now the most efficient way of discharging a capacitor, and you can see now the electrons are flowing the other way. Okay, they're flowing anti-clockwise, whereas before they were flowing clockwise. Okay, so we're discharging the capacitor. Okay. Now the best way to discharge, we are discharging a capacitor. Let me make sure I've got that right. Okay. Now we discharge the capacitor efficiently and safely by putting a resistor across the two terminals. Remember, we mentioned earlier that we had two cables, one coming from each plate. We would link the capacitor between those two terminals of a given value that would allow the capacitor to discharge. But remember that the resistor should be of a high enough value that the capacitors do not discharge too rapidly. Now, what is capacitance? The measure of the capacitor's ability to store charge is its capacitance. Typically, they store a much smaller charge than a power cell. Not quite. A capacitor can hold a charge for quite a high voltage, depending upon the size of the capacitor we're talking about. So in some cases it can be as small as a power cell, but in some cases it can be in thousands of volts discharge. So bear that in mind and keep safety aspects in mind at all times. Now, capacitance C is measured in farads. Now, in most electronic circuits, 1 farad is too large and much smaller values are used. The microfarad is the most popular, which we write as microfarad. This is 1/1,000,000th of a farad. Again here, it will be 1 times 10 to the minus 6, as I mentioned earlier. Okay. Here we have the formula. Charge and capacitance. Charge is Q equals I times T. Capacitance is C equals Q over V. Now, in due course, I probably will be doing some calculations on this, but bear with me. The main thing now is to provide you with the information and the formulas that you can begin to look at this for yourselves. Okay? A bit of self-learning at home never harms anyone. Right. Where are they used? Small value capacitors are used in tuned circuits and for coupling and decoupling radio frequency circuits. Now, medium value capacitors are used for coupling and decoupling various stages of audio frequency amplifiers. Large value capacitors are used in power supplies as they can smooth out ripples in the output of a rectifier. This gives you your smooth DC output when it goes through rectification, whether that be half wave rectification or full wave rectification. Okay. Now, polarized. Polarized or unpolarized. Small value capacitors are usually unpolarized, so they can be connected into circuits either way round. Electrolytic capacitors are polarized with a positive and negative terminal. These must be connected the correct way round in a circuit. Now, flux density. Now, that's a symbol for flux density. A unit of flux is defined as the flux which emanates from a positive charge of 1 coulomb. It is also measured in coulombs. So this symbol is equal to this symbol. Gives you the flux density. Okay. Let me be sure I've got this right, what I've said. Electric flux density, D, is the amount of flux passing through a given area that is perpendicular to the direction of the flux, vertical, and is measured in coulombs per square meter. D equals Q over A. Okay. Right, permittivity. Let's get it right. Permittivity. Let's say that again. This is a measure of resistance encountered by the formation of an electric field in respect of a capacitor. In in capacitor theory, it is seen as a measure of how an electric field affects or is affected by the dielectric, and is measured in farads per meter. It is given by the flux density divided by the electric field strength. Okay, now EO is the permittivity of free space, but it is considered to be in a vacuum. But as we do not operate in a vacuum, we have to make alterations for that and take that into account. Okay? Now, where the dielectric is other than a vacuum, the relative permittivity of the dielectric must be considered. So D equals relativity of free space times the relative permittivity of the dielectric. EO/ER is a ratio and is known as absolute permittivity E. Now here we have typical values of relative permittivity for given materials. Air is 1, polythene is 2.25, polystyrene is 2.4 to 2.7, paper is 3.5, glass is 3.7 to 10, rubber is 7, water is 8, T, ceramics is 6 to 1,000. And those are the relative permittivity of certain materials. Now that by no means is exhaustive, but that will do for us for now. And if you want to know the relative permittivity of a given material, you can now properly Google it, whereas we would have to research it in books many moons ago. Okay? Now, types of capacitors. Air-space variable capacitor. Now, two sets of meshed multiple plates separated by air. One set is fixed and the other is movable. So here you can see that one of them is fixed and the other one is movable, and that is what moves or rotates the part that is movable. That becomes your spindle. One set is fixed and the other is movable. As layers overlap, capacitance varies from minimum to maximum, okay? And by changing the plates. And again, remember that a capacitor consists of plates. So if we fix one plate and allow the other one to be movable, we can change the capacitance of that circuit. Now, fixed capacitors. Most capacitors have fixed values. They can be polarized and non-polarized. Polarized examples are electrolytic and tantalum. Non-polarized values are mica, plastic, paper, and ceramic. Now, there are quite possibly others which I have not mentioned, so bear in mind this is by no means exhaustive. So, capacitors in circuits, capacitors in parallel. Now, if we have capacitors in parallel, what we tend to do is to add the total capacitance. Okay, sorry, I've just shifted it over a little bit so we can get it full in. Okay. So it's Q total equals Q1 plus Q2 plus Q3. That's charge of the capacitors, remember, as we said earlier. But in parallel, they're simply added. Now remember that in respect of resistors, there is a difference in regards to resistors and capacitors. Capacitors in parallel is added as they would be in series, but in resistors in parallel would have your 1/over ratio, okay, or you have your reciprocal. And this is just the charge in regards to volt charge across the capacitance. Now, capacitors in series. And here, now it is always advisable for you to draw out diagrams. I find it very peculiar that students come into class and they seem to think that they don't have to draw a diagram. Oh, let me take a picture. Let me take a picture of this, or let me take a picture of that. The problem is that when they take a picture of it, they go away and they think that they're going to remember the picture, which does not work. Because if it was a simple case of taking a picture, I could take a picture of a book and I could become an engineer. But that does not work. You actually have to physically do the work for yourselves. Get the diagram drawn out, do the calculations, arrive at an appropriate solution. Okay. Dielectric strength and stored energy. Dielectric strength is the maximum amount of field strength that a dielectric can withstand. That is the voltage charge on the capacitor itself. And that is the charge held by the capacitor in regards to its dielectric. If the charge is too high, then the dielectric would break down. Therefore, the capacitor will then be useless to you. Okay? Dielectric strength is the maximum amount of field strength that a dielectric can withstand. E equals V over D. The energy stored in a capacitor is measured in joules and calculated later by the following. W watts equals half CV squared. Now you can simply make this 0.5 and you'll find that works out quite well in itself. Okay. Now here we have calculation time. Calculate the charge, voltage and energy values in each capacitor using the appropriate formulae. Now this is just a question for you to do yourselves, looking back at the information I've given you and the formulas I've given you. You should now be able to do this for yourselves. I will not be doing this for you, okay? And again, calculate the charge, voltage and energy values in each capacitor using appropriate formulae. And the formulae for capacitors in parallel you have been given previously, okay, and that was given here, okay, so use it. Just let's make sure that we have everything here, okay. And here we have a, well, I think people call it a compound network, but I just call it series parallel circuits. For these capacitors in series and parallel, calculate the charge, voltage and energy values for each capacitor using appropriate formulae. Again, apply the formulae. Begin to get familiar with using the formula for calculating capacitors. Again, when you enter this into your micro and into your calculator, it will be 3 times 10 to the minus 6, because it's 3 microfarads. Okay, nothing less. Your voltage here is 240 volts. So here you must resolve this parallel circuit first before you do anything else. So you leave that where it is at, and you then calculate this circuit here. Okay. Okay, and Now there's something here that appears to be missing. I've got a value for here, and we have value. Okay, now be aware that the values for this seem to have changed simply because my computer may not be compatible with the format that this was made up in, especially as I'm running Windows 10, and Windows 10 is not friendly with other systems. I will tell you that now for nothing, so do excuse me. But I do believe that should be 15 microfarads, that should be 3 microfarads, and this one here should be 2 microfarads. Okay, so again, 15 microfarads, 3 microfarads, and 2 microfarads. Okay, thank you for your time. Have a good day, and bye for now.